Hi everyone. This video is for the covalent bonding and organic chemistry lab. So I'm going to walk you through a little bit about what to expect and how to fill out your procedure as you go. All right. So as always, make sure you take a look at the entire procedure, you get all your supplies ready, and you have enough time to complete the lab. You can do a few of the parts individually, but once you get to the actual experimentation, you want to make sure you have some uninterrupted time to complete all of it. So starting out, your covalent bonding and organic chemistry lab is really going to be a big review about some of these topics we've talked about. So part A says, share your thoughts. You want to think about the term organic, right? Think about what it means in our daily lives. If you go to the grocery store and you buy organic produce, organic meat, what does that mean? Maybe you need to research it. Maybe you want to do a quick search online and see exactly what they mean by organic when you buy things at the grocery store. Okay. How do we use it in our daily living? Then think about what that term means in chemistry. It has a very specific meaning in chemistry. All right. So tell me your thoughts. What does it mean in both senses of the words? Write that down for part A. Part B is going to talk about ionic bonds. So it wants you to think about that ionic bond between a metal and a nonmetal. And take a look at question 1. It says metals tend to gain/lose electrons. Write the correct one in the box. Do they gain? Do they lose? You're going to do the same thing for nonmetals. Do nonmetals tend to gain or lose electrons? Write it down. And then it says because the metal and nonmetal have gained or lost an electron, they're both considered to be an ion. Therefore, they have an ionic charge. Okay. Remember that our opposite charges attract and like repels like, just like a magnet. Okay. So when a metal forms a charge, a nonmetal is going to have the opposite charge to attract to make an ionic bond. So number 3, when a metal forms an ion, is its charge positive or negative? And the next question asks about a nonmetal. Is it positive or negative? And remember your terms cation and anion. Your cations are positive ions, your anions are negative ions. So which one is which? And it talks through our table salt example, sodium chloride. Of course, that's a pretty good example. Okay, so read through that. And then number 5 says, when the nonmetal fluorine becomes an ion, what do we call it? So using the text right above, remember that we actually change the ending of the name when it becomes an ion. So using that above to guide you, what should you call ion of fluorine? Part C is then going to review covalent bonds a bit. So nonmetals can be very electronegative. Remember, our nonmetals are on the right-hand side of the periodic table, and the electronegativity increases as we go up and as we go to the right. Okay, so our nonmetals tend to be very electronegative. Electronegativity is the tendency to attract some electrons. So a high electronegativity means that there's a very high tendency to attract those electrons. All right. So this says what happens when two nonmetals bond? Two things with high electronegativity. Well, they're both going to be sharing those electrons then. It's going to form a very strong covalent bond. And so it's going to walk you through drawing some Lewis dot structures or some electron dot diagrams. Okay. Carbon, you can see, has 4 valence electrons. It's in column 4A. That's how we know that. And because it will be forming covalent bonds, it will actually share those 4 electrons. And it's going to want to reach the octet rule. So it's going to want to get 4 other electrons. That's why we say carbon can actually bond 4 different times. Scrolling down, we look at number 6, and there's going to be some other elements there. They want you to draw the Lewis dot structure. Okay. Remember, the proper way to draw the Lewis dot structure is to put 2 electrons on each of the 4 sides, but no more than 2. Okay. And of course, it talks about the octet rule. Maybe you want to highlight that. Make sure you save this and you can study from it. Right. The octet rule means it's the most stable when that valence shell is full, when there are all 8 there. And as a reminder, of course, hydrogen and helium are the exception. They only like to have 2. And then for number 7, you're actually going to draw a covalent bond between 2 chlorine atoms. okay? Now you might want to do this with both the Lewis dot structure and with the stick model. So if you remember the stick model we use for covalent bonding, one line, or stick, represents a shared pair of electrons between the two atoms, okay? So where will you draw the line between those chlorine atoms? Will you need one line, two lines? You could even have three lines, okay? So draw out what you think it will look like for two chlorine atoms to bond together, knowing that chlorine has the same electronegativity, right? Two chlorine atoms will be sharing those electrons, will be pulling those electrons very equally. All right. Once you get through part C, you're finished with the review and you're ready to start actually experimenting. So this might be a good time to pause and make sure you have all of your supplies ready. You're going to want to have an orange. This will also work with another type of citrus fruit. So if all you have at home is a lemon or a lime, that's okay too. So you want to have some type of citrus. You want to have your tea candle from your lab kit. You need to have a match or a lighter to light that candle. And then later on, you're going to be asked to use some marshmallows and toothpicks, or something similar to marshmallow and toothpicks, okay? If you don't have those, you can get creative. Maybe you have some other candies. Maybe you use some paper pieces, okay? So go ahead and gather your supplies. Go to the place where you want to do your experimentations. Remember, this is the area you talked about in your first lab. It's the place that has all of your safety procedures in place. You have a nice clean work area. You're going to tell your family to be careful, especially because we have a flame for this lab. Okay, so make sure that everything is going to be in a safe spot for your family. Make sure that you have a sink nearby to wash up. And I'll let you get everything settled before continuing on to part D. Okay, hi everyone. So now that you're on to part B, you're going to actually be experimenting. So again, make sure that you have a nice clean space where you can work and you let your family know that you're going to be doing your experiment so that you don't have anyone trying to touch your flame or interrupting while you're actually trying to get this done. So as a reminder, you are working with food today, but we're pretending that this is an actual lab setting and we never eat in the lab. Now I have to use my kitchen for my laboratory at home because it's the best space I have with a clean counter and a sink nearby to wash my hands. So if that's what you're doing as well, just remember to keep the area clean after you're done with your lab, wipe everything down, and make sure that you keep it as safe as you possibly can. Now we do say not to eat the orange or your marshmallows because you're going to be working with it, putting different chemicals and such on it. So do keep that in mind as you go throughout the lab experience. You will also find some lovely glasses in your lab kit. So you want to make sure you're wearing these anytime you do an experiment. Even though we're just using an orange today, it could still get juice squirted up in your eyes. We do also have flames and some reaction will occur. So I do suggest using your glasses. If you wear glasses just for everyday seeing, and they're nice and big lenses, it's okay to use just those, especially if these don't fit very well over them. Okay, so make sure you have your clean counter space and you have everything set up and ready to go. So for part D, it's gonna start off asking you to describe your orange. And again, if you do have another citrus, a lemon, a lime should work as well. But for step one, you wanna record some qualitative data. Remember, qualitative data are qualities. What do you see? What do you feel? Describe it. Quantitative data is numbers. So for this section, you don't need any numbers. You just simply want to talk about it. Is it round? Is it orange? What's the shape? What's the texture like? What's the smell? Okay. Is it heavy? Does it feel hollow? All these different qualities, go ahead and list out what you see in your orange for step one. Now for step two, we're actually going to get into our experimentation. So you'll need your little tea candle from your lab kit, and you're going to go ahead and light it. And again, make sure your space is nice and clear and careful. And I'm going to bring my camera down a little bit so you can see. And so once you have your flame lit, you're actually going to be peeling your orange over your flame. Now there's a couple ways you can do this. Your lab says that the best way is to kind of hold it in your hand and peel your peel up and over. You basically want to end up with your peel being over the flame, okay? However that needs to happen. And some oranges are harder to peel than others, huh? So here we go. Hopefully you can all see my flame being lit and getting my peel started. And as always, make sure you keep your hands away from the flame. Be careful about that. And so you can simply just peel it kind of up and over and see what happens with your spark. You might need to hold it there, move it around a little bit. Okay. And you want to look at anything that might be happening. I'm not sure how well my video picked that up, but hopefully you saw it. You want to be looking at anything that's happening with your peel, with your flame. Okay. You can try it a couple different times. You can peel it, especially if you have a nice big orange. Peel it a few different ways. Again, the more samples we get, the better our data. And it helps if you have an especially juicy orange. All right, so that's the method you're going to be using. You're going to be taking your orange, holding it over your flame, and seeing what exactly happens. Okay? And again, you can try it with a couple different peels, try it a few different times. You then have a box in part D for your observations. So write down what you saw. Maybe you saw something happening with your peel. Maybe you saw something happening with your flame. Make sure to record all of that. All right, once you've completed your lab with the orange and the flame, you can go ahead and wash that juice off your hands, blow out your candle, make sure it's nice and safe and pushed back, and then you can continue going with part D. So part D is going to talk a little bit more about organic chemistry and the molecules that we bond with covalency. So it says organic chemistry is the study of carbon. It turns out that carbon compounds are also the study of life, right? All living things have carbon in them. So that's why we focus on it so much. Carbon-based life form is what exists on this earth. It's incredibly important to understand how carbon can interact chemically. Organic chemistry is the largest area of organic chemistry is the largest area of chemistry. In our daily lives, organic might mean natural, maybe without chemicals. But for chemistry, organic means the study of carbon and its compounds. So for question number 3, it says, how many times can carbon bond? Go ahead and write your answer down. And then it kind of walks you through it down below. So carbon holds its bonds very tightly, which allows carbon to make very long, stable chains of molecules. Carbon can bond with other carbon and make very long polymers, big molecules, with repeating subunits. And we're going to look at a few different examples of some carbon organic compounds. When we make organic compounds with just carbon and hydrogen, we call them hydrocarbons. And hydrocarbons can be very large in their size. We can have a whole lot of carbons bonded together. But remember, carbon always wants to have those 4 bonds, those 4 lines coming off of every carbon, because that means it has a complete outer shell. It has 8 valence electrons that it's sharing to help complete it. So keep that in mind as you do the following problems. Now it says carbon can bond 4 times, but hydrogen, on the other hand, really only needs to bond once to get that 1 extra electron to get to its 2 full valence shell. Review the diagram from part C number 2 for methane, CH4. And we see here that we have 1 carbon bonded to 4 different hydrogens, which makes everyone happy in that equation, right? Our carbon has a complete valence shell, the hydrogens have their complete valence shell. We can draw that with our stick model, those lines, each line representing a shared pair of electrons. And of course, that's just a representation. There's not really a stick between the atoms. Okay? but the bond is formed when the atoms share the electrons and the outermost energy levels of electrons are touching. Now take a look at number 4. In the following space, you want to draw the first 10 hydrocarbons. So each time we add a carbon onto the chain, and we're going to get up to 10 hydrocarbons in this. You can see the first 2 completed for an example, and you just need to follow all the way down. You can draw this straight on your computer. Maybe you draw it on some paper, and then you go ahead and put it into your document. However you need to do it is fine. Now you can see for methane, you have 1 carbon. Ethane is going to have 2 carbons. Propane will have 3. So you see a pattern starting to form. Butane will have 4. Maybe you realize pentane has a prefix of pent, P-E-N-T, meaning 5. So you probably have 5 carbons. And you keep going all the way down until you have 6 carbons. Now you need to write the molecular or chemical formula. So you need to figure out how many hydrogens will go with each carbon. Okay. You can do this by drawing out the molecule first and then counting them up. And so for methane, you have 1 carbon. It needs to have 4 lines coming off of it. So you have 4 hydrogens. When you look at ethane with your 2 carbons, you notice that every carbon still has 4 lines coming off of it. We only have 6 hydrogens then, but everyone is achieving their octet rule. Every carbon has those 4 lines coming off, and your hydrogen really just needs the 1 line for the duet rule. So let's do propane together as well. So propane, I said, has 3 carbons. So you're going to start off by drawing 3 carbons bonded together, just like that. You should always start with your carbon backbone before adding all of your hydrogens. Now, how do I know how many hydrogens to add? I just have to draw the line so that every single carbon has 4 lines coming off of it. And remember, they can share lines, of course, because this is covalent bonding. So there you go. Those are my 4 lines coming off of every single carbon for propane. Now to finish propane, I'm going to have to add H's at the end of all of those sticks. Because this is a hydrocarbon, all I have to work with is carbon and hydrogen. And so my propane drawing should end up looking something like this. You can then count up how many you have for your molecular formula. So I have C3 and H8. So go ahead and try that with the rest. You're going to go all the way down to 10 carbons bonded together in the backbone. And remember, start out with your carbon backbone first, and then go back and add all lines so that you have 4 lines coming off of every single carbon. Okay? You should know these for the exams. You should be able to draw them out. You should be able to recognize them. And all of these are what we call saturated. So when it's saturated, it means that you have a carbon with hydrogens attached to it. You have single bonds between every single carbon. Okay, so for right now, just know you have single lines going between every single carbon. After you finish that table, scroll down a little bit. And it says you might recognize the names of some of these hydrocarbons. Hydrocarbons are the main source of energy for a lot of what we do as humans, right? We use methane in our natural gas. When you go to put gasoline in your car, it's actually a different type of hydrocarbon. So take a look next time you go to fill up, okay? You'll start to notice octane being listed, all of these different names you might have heard before. These hydrocarbons are called alkanes. Okay, that word is highlighted for a reason. You might want to make a flashcard for that. Your alkanes have single bonds. So like we said before, you have single lines going between all of the carbons. That means they are saturated, meaning they have the maximum number of hydrogen atoms that they could possibly have. Okay. Now, we can also bond carbon with double bonds or even triple bonds, which is what you see in the bottom right corner of this page. So it says the gas that you squeezed out of the orange peel was actually ethylene. Okay, that's the drawing right there. That's what came out of that orange peel, and hopefully your candle did it too, but if you noticed, there was a spark when you held that orange peel over the flame. If you didn't see a spark, hopefully you saw it in my video, and hopefully you still have some orange peel left. You can try it again. Why not? but you should have seen an actual spark, a jump of the flame. And that's because you squeeze some of that ethylene out into the flame, and it caused that organic chemical reaction. Ethene, if you notice, has an E instead of an A. Okay, so ethane is an alkane with single bonds. That's what you drew up above. But here we have ethene with an E. So this is called an alkene. And alkenes have at least one carbon-to-carbon double bond. You can also have a carbon-to-carbon triple bond, and that's called an alkyne with a Y. So I'd make sure you know those three terms, alkane, alkene, and alkyne. They have to do with the bonds between carbon if they're single, double, or triple bonds. Okay. And you're going to scroll down to number 5. It says draw pentene, the chemical formula, and draw out what it would actually look like. Now pentene, you see, has an E, so this means it has to be an alkene with a double bond. Okay. You need to have at least one double bond between your carbon atoms. You can put it at any carbon atom, okay? It's not telling you specifically which one to do, so you can pick any of them. Now, if you look up above in your table, you already drew out pentane with an A, and pentane had 5 carbons, and so will pentene, right? That prefix did not change. So you should still have your 5 carbons, and you're gonna pick one of them, any one of them, to draw your double line. Now you have to go back and still add in all of your other hydrogens. Remember, this is a hydrocarbon, so you can only use hydrogen and carbon. And you still want to make sure that every single carbon only has 4 lines coming off of it. So you might notice that you'll have less hydrogen. So depending on where you put your double bond, your pentene might look a little bit different than mine. But you'll notice that this pentene has less hydrogen, right? Because my double bond is taking up some of the space. So this is considered unsaturated. Alkanes are saturated because you have the maximum number of hydrogens that could possibly be added to the carbons. But alkenes and alkynes, on the other hand, will have less hydrogen and will be considered unsaturated. So draw pentene. Again, you can put that bond wherever you'd like. Maybe you put it between your first carbons, and that works out just fine too. If you do that, your structure will end up looking like this, and then you go back and add your H's, okay? And we name these based on the number of spots between the carbons where you put the double line. So in my first example, I put it in the second spot. So this would be 2-pentene because it's in spot 2. Whereas my example down below, I put it in the first spot, so that would be 1-pentene. Okay. All right. There is an easier way to draw these. And so instead of drawing out every single carbon, all you have to do is draw it in forms of lines. Let me show you what I mean. For methane, it's too small to do. Methane will draw out with all of the carbons, okay? But let's look at butane, for example. Butane, if you go back to your chart, has 4 carbons. And so I could draw out all 4 of my carbons down here, okay? Or I could know that I'll have a carbon in every single one of these spots, and I could simply draw it as a line. So this right here is butane. I don't have to fill in all of the other spots with carbons and hydrogens because I know that these all represent single bonds of hydrogen and carbon. If I have butene, I could simply draw my double bond that way. So we can use this to represent the hydrocarbons instead of drawing out every single carbon in there. Let me show you pentene as an example. So each end of the line is a carbon, okay? So this is a carbon, 2, 3, 4. There's my 5 carbons. And I could make this pentene by drawing my double bond there. So you might see that drawn out, and it's just a faster way of doing it. Especially when you get into hexane, nonane, decane, right? To draw decane, I could simply draw it like this. Right? I just need to make sure that I have my 10 carbons represented by these 10 points. 1, 2, 3, 4, and so on and so forth. And if I add a double bond, I simply note that. Okay, so you've completed number 5 of part D. We're going to scroll down a little bit more, and you're going to go into your next experiment, which is really a good way of modeling some things out for those of you who are visual and kinesthetic learners. So you'll need your marshmallows and your toothpicks for this, or something similar. Okay, so for this next part, you're going to be modeling some of these different hydrocarbons with your marshmallows and toothpicks. So I'm going to bring my camera down so you can see. But what I want to do is I want to make sure that I have a very clear difference between my carbons and my hydrogens. Maybe you're using some colored marshmallows. Maybe you want to actually draw on your marshmallow. Remember, we're not eating them because we're experimenting with them. So maybe you get a marker and you denote which ones are your carbons, which one are your hydrogens. You could also use something like a jelly bean, something you can stick a thing into. Maybe you use some blueberries, anything like that. And for your first one, it says you want to make butane, okay? So to make butane, maybe you go back up to the top of your chart and you figure out how many carbons butane has. And you're going to replicate it with your carbons and with your hydrogens, whatever you're using as your model. So let's do butane together. Butane has 4 carbons. So I'm going to get out my 4 very sticky marshmallows. Okay. And I'm going to use my toothpicks to connect them. These are going to be my double bonds or single bonds or triple bonds, however many I put in. But they're going to be representing the shared pair of electrons. Now you want to model it just like you would draw it. So we want to make our carbon backbone first. And remember, butane has 4 carbons. So I'm going to stick 4 of my marshmallow carbons all on a stick like this. Now I can clearly see that my carbons are sharing electrons with each of my toothpicks. And then I need to go back and fill this in with hydrogens. So if you recall, every single butane is going to be an alkane, right? Which means that it's saturated. It has as many hydrogens as it could possibly have because we only have single bonds between the carbon. So I'm going to grab my hydrogen and I'm going to add them on to all of my different carbons to make sure that I have 4 bonds for every carbon. Okay, so now I've went ahead and I've started adding all of these different hydrogens onto my carbons. Now remember, as you do this, you're going to want to take pictures of your models to upload to your homework and also to help you study from later. Because again, we have a lot of people in the class who learn best by doing hands-on things and by visualizing. So hopefully this will help you out. So I decided to go ahead and use blueberries. So my blueberries are my hydrogens, my white marshmallows are my carbons. And so I can clearly see this is butane. I have my 4 carbons and I have hydrogens attached to every single one to get 4 total bonds. Okay. I only have 1 toothpick between each, which means they're single bonds, which means it's an alkane. Now your next problem asks you to make butene with an E, which means you're going to have to add a double bond. So again, I can put the double bond between any of the carbons. Okay, this would be butene in the first section, so 1 butene. If I put it here, it'd be 2 butene. And if I put it here, it would be 3 butene. Okay? So I'm going to go ahead and put it in the third spot. We'll call this 3 butene. And so I'm going to add my double bond between these marshmallows. Okay. Now this is incorrect. I have to change something else, right? Because this carbon has 4 bonds. Oop, it's sticky. That carbon has 4 bonds, so it's good. This carbon has 4 bonds, so it's good, okay? But this carbon, because I added an extra toothpick, I now have 1, 2, 3, 4, 5 bonds. How can I fix that? Well, I'll just take away a hydrogen. And what about this last carbon? I have 1, 2, 3, 4, 5. So I'll do the same thing. I have to remove a hydrogen. So this now is my correct butene model. So you're going to go ahead and do this for the rest of the questions, and you're going to make sure to take pictures of all of your models afterwards, okay? Okay, so once you finish up with your marshmallows and whatever else you use, go ahead and clean up your table, wash all that stickiness off your hands, and then we'll continue on to part E. So part E is talking about finding the average atomic mass. Okay. The average atomic mass, as we know, is listed on periodic tables. It's that decimal number, and it's a decimal because it is an average of the isotopes that exist for the element. Now, of course, isotopes are the exact same element, so they have the same amount of protons, but they have a different number of neutrons. So that average atomic mass can help us figure out the relative abundance of these different isotopes in nature. We're going to be looking at carbon, okay? Carbon has 3 different isotopes that could occur. And remember, we named the isotopes by the rounded whole number, rounding that mass to the whole number. So carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. And carbon-14 has 6 protons and 8 neutrons. Generally, carbon-12 has a mass of about 12, right? Our mass is roughly the protons plus the neutrons. However, neutrons and protons are slightly different in their masses, so that's a bit of a generalization. Electrons also have a bit of a mass, but they're so negligible that we kind of ignore them in our purposes, all right? So you can see that there is a more exact mass for these elements listed here. So these are the big decimals you see in your table. And it says we're going to be using this exact mass to help determine the average atomic mass. So what you're doing for this part is you're essentially trying to find the numbers that are listed on the periodic table. You're going to try to work through it by yourself to get an understanding of how the scientists put these numbers on the periodic table and the purpose of them. So to find an average, we must give the proper weight of each isotope, which we have in the table above. If you were to take a sample of naturally occurring carbon, you'd find that carbon-12 is the one that occurs most frequently. It's found 98.9% of the time. But every now and then, we'll find carbon-13 and carbon-14. So they have to add in a little bit to the actual mass, right? They do count, just not as much as carbon-12. So it says carbon-12 makes a larger contribution when determining the average atomic mass. And carbon-14 really will not be included at all. It's such a negligible amount. It's so rare that that occurs in nature. So it says, since 98.9% and 1.10% are parts of 100%, we're going to consider both of these values to be accurate to 5 sig figs. Okay? You can use the same rationale on the calculations below. So you're going to be using 5 sig figs for these problems. Now it gives you an example. It walks you through how to find the average atomic weight for carbon. Your procedure, you're going to multiply the exact weight of that isotope by its percent abundance. So the exact weight of carbon-12 is 12.00000 times the percent abundance. We're going to put this in a decimal form so we can multiply. To put it in a decimal form, we just move the decimal to the left 2 spaces to get 0.98900. That's our 5 sig figs. To get an average, remember, we add all the parts together and then we divide. So this is essentially what we're doing here in the problem. We're multiplying the average atomic mass for that isotope, or I should say the exact atomic mass for that isotope, by its percent abundance, and we're adding it to the other isotopes. Now again, walking through this problem, maybe you try it out on your calculator, and you get to the answer of 12.011. AMU is average atomic mass unit. That's the unit we use on the periodic table for these weights. Okay, now remember to round your answer to 5 sig figs. So you're going to try that for nitrogen. So you have 2 different isotopes for nitrogen, one with the mass number of 14, one with the mass number of 15. So nitrogen 14 and nitrogen 15. You're going to take the exact weight, 14.003074. You're going to multiply it by 0.9963. And then you're going to add that to 15.000108 times 0.0037. Now make sure you're using order of operations here. You should be doing your multiplication before your addition, and then make sure that you round your answer to 5 sig figs and include your unit AMU. Then you're going to scroll down, you're going to try it with chlorine and with silicone. And then you've completed the lab portion. If you keep scrolling down, you have an analysis to complete, which are some questions about what you did today. So take some time to read through and make sure you answer those as accurately as you can. Your analysis is going to be asking you to classify compounds as organic or inorganic, meaning not organic. Then it's also going to have you draw a cyclohexane. Okay, now we haven't drawn things in a cyclical form yet, but it's the exact same as if it was stretched out in a line. So use the exact same rules for when you put all your marshmallows and toothpicks together, and just think about connecting it into a circle. Maybe you want to do this with marshmallows and toothpicks just to see how it goes. But take your best stab at it, try to draw cyclohexane, okay? And then that should be the end of your lab. As always, email me with any questions you might have, and have fun.